Hello everyone, I'm Dr. Buddhika Liyanike. So today's topic is electronegativity and the bond polarity. Let's go and find out the covalent compounds, electronegativity and bond polarity. What is the meaning of electronegativity? Electronegativity refers to the ability of an atom to attract electrons in a chemical bond. Or simply we can say the favor for the electron. This is a electronegativity table. You can see for each element there's a specific value assigned. For fluorine 4.0, oxygen 3.5, nitrogen 3.0, and for metals located left hand side they have some lower values compared to the non-metals. Metals have lower electronegativity than non-metals because metals are less favor electrons. Metals likes to lose electrons, always forming a positive charge ion, or we call cations. Non-metals, on the other hand, they likes to gain electrons. They favor electrons. By gaining electrons, non-metal form anions or negative charge ions. Then what is the periodic trend of electronegativity? Electronegativity increases when we move across the period from left to right. The reason is metallic character is decreasing. Metals are located left hand side, non-metals are located right hand side. If we move across the period, metallic character is decreasing, therefore electronegativity is increasing. The favoration for electrons increasing. And from top to bottom, electronegativity decreasing. Again, the reason is metallic character is increasing when moved from top to bottom. Therefore, favoration for electrons decreasing. Fluorine is the highest electronegativity element, and you can see here the commonly used elements and their electronegativity. Fluorine 4.0, oxygen is the next largest, nitrogen and chlorine same, carbon 2.5, hydrogen 2.1. So why we need these electronegativity values? To determine the bond polarity. Let's find out how we can determine bond polarity using electronegativity values. Bond polarity. We can determine the polarity of the bond by examining the difference in electronegativity between two atoms. Let's take these three examples: fluorine F2, hydrogen fluoride HF, sodium fluoride NaF. If we calculate the difference in electronegativities, we can determine are they covalent, polar or non-polar, and ionic. Fluorine. One fluorine atom 4.0, the other fluorine atoms 4.0. So fluorine, fluorine, two fluorine atoms, in between one covalent bond, two electron sharing. So electronegativity difference is 4.0 minus 4.0. It is 0. So 0 difference means the bond is non-polar covalent. Meaning is electrons, two electrons in between two fluorine atoms are equally sharing between fluorine atoms. Therefore, it is non-polar covalent. Next one, hydrogen fluoride. Fluorine 4.0, hydrogen 2.1. Then 4 minus 2.1 is 1.9. This is we call polar covalent. Polar covalent meaning is electrons are not equally sharing. So two electrons share in between hydrogen and fluorine, but electrons are more closer to fluorine, most electronegative element, than hydrogen. So there is some charge separation in this HF molecule we call polar covalent. Next one, sodium fluoride. Sodium is 0.9, fluorine is 4. So 4 minus 0.9 is 3.1. This is to be called no longer covalent, this is ionic. Covalent means electron sharing, ionic means transfer electrons. So transfer electrons from metal to non-metal. The HF molecule. HF molecule Hydrogen is less favor for electrons. Fluorine is the highest electronegative element, more favor for electrons. So electron density is more closer to fluorine than hydrogen. Then there's a partial charge separation due to that unequal electron sharing. The partial charges we can indicate it by this delta sign. Delta minus penetrate next to fluorine and delta plus charge penetrate on hydrogen. This unequal distribution of partial positive charge on hydrogen and partial negative charge on the fluorine atoms. This is we call partial charge separation or polar bond between H and F. So what is the criteria for bond polarity? Nonpolar covalent. Nonpolar covalent electrons share equally between atoms. The previous slide you notice F2 molecule. In F and F electrons are equally sharing, then we call it is nonpolar covalent. What is the limit? If the electronegativity difference is less than 0.5, then we called the bond is nonpolar covalent. Polar covalent. Electrons are not equally sharing. Still electrons are sharing the covalent bond but not equally sharing. Limit is between 0.5 to 1.9. Electronegativity difference between two atoms in this range we call polar covalent. Ionic bond. Ionic means no longer sharing electrons. This is transfer electrons from metal to non-metal. If the electronegativity difference between atoms greater than 1.9, then we call the bond is ionic, not covalent. So these are the guidelines or the criteria to determine bond polarity, whether they are non-polar covalent, polar covalent or ionic. Let's talk about the dipole moment. The polarity of HF molecule can be indicated in two different ways. The one way we discussed in the previous slide, the unequal distribution of electrons penetrate partial charges delta minus on fluorine, delta plus on hydrogen. The same concept we can represent in another way using this cross arrow. The meaning of this cross arrow, the cross end of this arrow is the positive end of the molecule. The head part of the arrow indicates the shift in electron density towards fluorine atoms. Electrons in this covalent bond shift towards fluorine indicated the head part. Those are two different ways we can indicate the polarity or the charge separation or unequal distribution of the electrons. Then what is dipole moment? A quantitative measure of this polarity we called dipole moment. It's a quantitative measurement. We can use this formula to calculate dipole moment. Dipole moment symbol is mu, mu, mu. Mu is equal Q times R. If mu is dipole moment, Q is the product of the charges, cation charge times anion charge. R is the distance between cation and the anion. For example, here cation charge, hydrogen charge and anion charge is fluorine charge. The distance between hydrogen and fluorine we called R distance. Dipole moment units is debye or uppercase D debye units. 1 debye is equal 3.336 times 10 to the negative 30 coulomb meter. So you need this formula and this equality calculations of dipole moment. So let's practice some examples in the next slides. Practice problem solving. We learned three concepts: electronegativity, and then using electronegativity, how we can determine bond polarity, and then dipole moment. So let's apply those three concepts in these questions. The first question is, which of the following bonds are polar? There are three bonds are given. The strategy here is calculate the electronegativity differences between two atoms. This is the criteria. If the bond is non-polar covalent, difference should be less than 0.5. If the bond is polar covalent, the difference should be in between 0.5 to 1.9. Ionic is greater than 1.9. So let's apply one by one. First one, lithium and fluorine. So fluorine is 4.0, lithium 1.0. So 4 minus 1, difference is 3.0. This is greater than 1.9. Then the bond between lithium and fluorine is ionic bond. Electron transfer from lithium to fluorine. Second one, the bond between chlorine and chlorine. So chlorine is 3.0, 3.0 minus 3.0, 0 difference. Zero difference is non-polar covalence. Electrons in this covalent bond equally sharing between two chlorine atoms. Next, the bond between selenium and oxygen. Oxygen is 3.5, selenium is 2.4. The difference is 1.1. This is in between polar covalent region, 0.5 to 1.9. So this is polar covalent bond. Electrons are sharing but unequally. Fourth one is the bond between hydrogen and iodine. Hydrogen is 2.1, then difference is 0.4. This is non-polar covalent because 0.4 is less than 0.5. It is non-polar covalent. Question number 2. Classify the following bonds as polar, non-polar or ionic. There are two molecules given here. First one is hydrogen sulfide, H2S. Second one is H2O2, hydrogen peroxide. These are the molecular structure of H2S and H2O2. In hydrogen sulfide, it's like water molecule bent shape. Sulfur is the central atom, two hydrogens attached to sulfur, and there are two lone pairs on central sulfur. Hydrogen peroxide, two oxygen atoms are the central and hydrogens attached to each oxygen. Now, S bond. HS bond electronegativity difference is 0.4, less than 0.5, this is non-polar covalent. And in H2O2, OH bond difference. 3.5 minus 2.1, this is 1.4, polar covalent bond. OH bonds are polar covalent. The next type is bond between oxygen and oxygen. The difference is 0, so it is covalent, non-polar covalent. So oxygen and oxygen is non-polar covalent. Oxygen hydrogens are polar covalent. But in H2S, all two bonds, both bonds are non-polar covalents, no polarity. Third example. Using the data given in the table, calculate partial charges on hydrogen and bromine NHBr molecule. HBr molecule bond length is given in angstrom unit. Dipole moment is given in debye units, 0.82 debye. The first step is unit conversion. We need to convert angstrom into meters. This is the equality. 10 to the power 10 angstrom is equal 1 meter. So let's convert 1.41 angstrom into meters. Then it becomes 1.41 times 10 to the negative 10 meters. Next unit conversion is debye. 1 debye is equal 3.336 10 to the negative 13 coulomb meter. So let's apply for 0.82 debye. Then it becomes 2.74 times 10 to the negative 30 coulomb meter. Now we convert units into our desired units, meter. Now let's apply the formula. Dipole moment is equal charge, cation charge times anion charge is Q times the distance R. So if we rearrange this equation, we need to find Q. We have mu and R value is given. So mu value, after we convert the units, it is 2.74 times 10 to the negative 30 coulomb meter. And our R value is 1.41 times 10 to the negative 10 meters. So after we solve this, Q is 1.94 times 10 to the negative 20 coulomb. Now, We want to convert this coulomb into electronic charge. The equality is 1.6022 times 10 to the negative 19 coulomb. We called 1 electronic charge. So let's convert the Q amount we calculated in coulomb into electronic charge. This is 0.12 electronic charge. The meaning is in HBr molecule, hydrogen charge is plus 0.12, bromine partial charge is negative 0.12. So these are the partial charges on hydrogen and bromine in HBr molecule. Thank you all for watching. Please don't forget to subscribe to the channel, and I like to hear your comments and ideas.